Okay, so this video is going to be the last one of this homework. It kind of takes care of some loose odds and ends. The first topic is what I like to call charge superposition. I don't think that's the official name of this topic or anything, but it's the best thing I can think of to call it. So this is basically just like a really handy trick that you can use to do some problems. Let me kind of explain how it works by kind of leading up to how, what it's based on. So like in homework 1, we had a couple different charges, let's say plus Q1 and plus Q2. And if we wanted to know, say, the net electric field at some point in space, well, the net electric field, of course, is just, okay, what does charge 1 have to say about that? If these are both positive charges, they'll both contribute away, radially away. Charge 2 says that electric field should point like that, and of course the net electric field is just going to be the vector sum of those two contributions. That's what we call field superposition. We're essentially saying that the net field at this point in space is the vector sum of all the contributors, and that's old news, not controversial at this point, and that works when you have extended charge distributions or continuous charge distributions as well. You've already done this in homework 2, so I guess I can label this as homework number 1. That was kind of the point charge homework. In homework 2, let's see, you had stuff like this. You had like, okay, I have a finite line charge like this, and I have a finite line charge like that. I can't remember the exact problem, but something like that. You want to know the electric field here. Okay, well, this is, let's see, this is a charge Q1, this is charge Q2. Q1 contributes this way because it's positive, and then Q2 it's negative, so it contributes towards it, so it's that like that. And again, same deal. If you know the formula that each one of these makes, then you can just do the vector sum of them to get the field, same deal. The only thing that's really changed is that what's contributing the individual fields are now not point charges, but they're some other continuous things. We learned about finite and infinite line charges, infinite planes, solid disk, all that stuff. And of course, that same stuff can be said with Gauss's law as well. Let's say I have, this is now a sphere of charge. So we have a uniformly charged sphere, let's say total charge plus Q1, and I'll draw it in a different color here. Let's say I have another second charged sphere, trying to show it's a sphere, not a disk, and that says total charge minus Q2. And if I want to know the electric field at this particular point in space, let's say this one is E1 radially away, and this one is E2 radially towards, so on and so forth. But let me show you that there's a kind of a cool trick. Let's say that these two spheres are so close to each other. Let's say it looks like this. And I guess one thing I should specify is that they not only have the same total charge, but let's say they have the equal and opposite charge density. So plus rho over here, and the minus rho. And let's say they're close enough to each other that they actually overlap. So now the charge itself is superimposed on top of each other. So that's what I mean by charge superposition, is that you're literally putting charge in the same region of space. Now, this is the region of space that I'm interested in here, this one where they overlap. And it has both positive rho and negative rho. And what that actually means is that the overall charge density here, plus rho and minus rho, is actually 0. So this region of space actually has no charge at all, okay? And so what we've essentially done is, let me try to recopy this. We have found the charge distribution of a very, very strange looking charge. We have found this kind of we have created a charge distribution that's sort of like a kind of a butterfly shape almost, with like this kind of hole here with no charge. Now, whether or not there's actually material here that's neutral, or this is just completely empty space, doesn't really matter. There's no charge there. Now, if I were just to give you this, you might go, how would I find the field of that? Well, remember that essentially this is made out of two simpler charge distributions. So just the same way as over here, I can just find what's the field of this, what's the field of this. If you are asked for the electric field here, the net field, you just take this vector sum of this field plus this field, and it actually is equivalent to this, okay? So the trick here really is that if you have these kind of funky holes or any kind of weirdness in there, the question is, can you make this weird charge distribution, has holes, etc., so on and so forth, out of a superposition of easier charge distributions? And if you can find the field by adding if you can make the charge, essentially make the charge by superposition, then you can actually get the field of it by superposition as well. So that's essentially the trick. So essentially anytime you have a sort of weird charge distribution on the homework, you're not going to directly integrate it. Like if that's not going to work, it's going to be too difficult. Like on homework 2, that's not going to work. And if you can't use a direct application of Gauss's law because it doesn't have the necessary symmetry, like in the rest of homework 4, well, consider charge superposition as a trick so that you can essentially make your weird charge distribution out of some combination of your previous techniques, okay? And so this is a really useful trick, especially with holes and stuff like that, because with holes you can always make them out of a superposition of equal and opposite charge density. So the big giveaway, if you have a hole of some sort, it's worth trying, and especially if that hole is not radially symmetric. So of course radial symmetry is required to use Gauss's law just in its raw form. So if your hole is not radially symmetric, that's a dead giveaway that maybe this trick would be useful. It is useful in other applications as well. Just kind of think, if you have some really strange looking charge distribution, then can you make it out of simpler ones, just stacking them on top of each other? In any shared regions of space they have, of course, what's going on will just be what is the sum of the two simpler charge distributions, like so. So that's just a really handy trick. It does come up a couple times on homework, and it is a nice trick to throw in on exams because essentially you get some really strange charge distribution and you try to figure out what its field makes. These are the kind of the three different things that that you can do. You can use just this, thus this, or the charge superposition is kind of like using the previous tricks or the previous techniques, but then also kind of stacking them on the charge distributions on top of each other. Okay, and then the other final order of business, I want to go back and revisit charge polarization. So charge polarization was at the beginning of homework 2, and as you can recall, it was highly conceptual. And the reason it was highly conceptual is because actually doing the math in a general case is really hard and beyond the scope of even this class. Let me remind you, for instance, if I had a positive charge and then I brought a neutral conductor nearby, we learned that in a neutral conductor, the net electric field inside, E net equals 0 inside, this was the idea of perfect shielding, and we essentially learned that the interior of the conductor is protected from any net field, and the reason again is that if it wasn't, the charges are free to move till it was. It's just charges will flow until they no longer want to, and then you get this charge superposition. You got a minus Q that goes onto the left-hand side, positive Q goes onto the right-hand side in this particular case. The sum of these two is still 0 because the conductor is still neutral, but the charge has polarized to make sure that the net field is 0 inside. Now, we addressed that as a concept, but as far as how much charge is here, that is very hard to calculate, okay? So what the amount and the exact distribution of charge in the polarization, that is hard to figure out in a general case, okay? So it is very tricky. However, what I'm going to do is I'm going to take a look at a single special case that we are now equipped to address where we have complete radial symmetry. Okay, spherically, it's going to be a spherical radial symmetry, and that, of course, gives us a lot of techniques from Gauss's law that we did not previously have access to. And so let me go ahead and show you. This is obviously not radially symmetric. You have a charge on the left, and this is on the right. So this is not fully radially symmetric, even though these charges themselves, I've sort of drawn them as spheres. Obviously, this charge distribution is now not radially symmetric. So let me show you how we're going to do this. So I'm going to do is my charge here, this charge here that's just going to be, all it does is sit there and cause the charge polarization. That's going to be a point charge. Okay, I guess I can call this, I'll call this Q1 here, and I'll call it Q1 over here, just so you know kind of what corresponds to what. And then this neutral conductor, this is going to be interesting. It's not going to be to the side of the Q1. It's actually going to be surrounding Q1. So this is the first time where we've caused the charge distribution, caused the charge polarization in a neutral conductor that's actually going to surround this. And I'm going to do my best to draw this completely radially symmetric. So this right here, and I'm going to try to color it in lightly just so you see where the material is. Okay, this right here, this is my neutral conductor, and I guess I'll draw it, this one the same color, just so you can see the corresponding pieces. So this is the first time that we've actually taken the charge that causes the charge polarization, we've put it not to the side of the neutral conductor, but inside. And in fact, it's right in the middle of this. Okay, so what do we have here? This is a kind of a spherical conductor with a hole in it, or cavity, and right in the center of that cavity, we have the charge. So here's what we're going to do. Let's work out the charge polarization. Now, instead of a left to right polarization caused by a charge on the left, this is actually going to be an inside-outside polarization caused by the charge on the inside. So what's going to happen here? This is going to charge polarize, and instead of the negative being attracted over here and being attracted to the left side, now those negatives are going to be attracted to the inside. Okay, so that right there, I drew them in blue, and for the moment, I'll label this as minus Q2, minus Q2. We'll see how Q2 and Q1 relate. I guess I should call it Q2 over here as well, just so that we can have the corresponding stuff all kind of labeled. I'll do those in blue. I do recommend you do this in a different color if you can in your notes as well, because otherwise it gets very confusing. And then, of course, if there's a minus Q2 pulled toward the Q1, then there will be over here as well, same thing. There'll be a Q2 that's positive, in this case, that's on the other side, plus, plus. So let me try to draw the same number. I do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12-ish. I'll just try to draw roughly the same. I lost count already. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then, of course, the biggest thing that I can do to remember that they're equal and opposite is to label that as plus Q2, okay? So here I have it. I have this this green conducting shell, okay, is still neutral, because while the charge has polarized into minus Q2 on the inner edge and plus Q2 on the outer edge, the overall charge is still 0. Same reasoning as over here. Okay, so now what? Let's go ahead and work out what has to happen here. So here we can use Gauss's law. Gauss's law. Oh, and I guess I should probably start by drawing some of the fields made by these guys. So Q1 is a point charge, and I drew that as black, so I'm going to draw this as black. I'm going to draw some lines out of here. 1. I guess I'll do my standard 8 lines. Okay, and notice that I did draw them from the point charge all the way to infinity, okay, because that charge alone, just that's the field it makes. There are going to be other fields which are going to make E net be different, but this is just the point charge so far in the middle of that cavity. And let's go ahead and do some of the other ones. Now, here's where we really can rely on our experience of Gauss's law. So on the inner edge, we have minus Q2. And this is in a spherically symmetric pattern. We have done this already. So we know that if you have a shape like this, oh, I didn't draw it in blue over here. I guess I probably should have. This is the blue part. So the blue part, this is minus Q2. By Gauss's law, refer to the previous videos in this homework. So if we draw ourselves our Gaussian surface in there, we have that there's no enclosed charge. Remember, we're just talking about this part. And so we have no enclosed charge. Q enclosed is 0, and we have our necessary symmetry, and that allows us to deduce that the electric field is 0. Okay, so there's no electric field caused by this charge inside, and then outside, if we drop our Gaussian surface out here, okay, so this is inside, and then outside, Q enclosed is Q. That's so the Q enclosed is 0. In the inside, but on the outside, Q enclosed is minus Q2, and that of course leads to the electric field not being 0 on the outside. In fact, we know that in this spherical radial symmetry, the electric field will be exactly that of a point charge of a value Q2, or negative Q2. So that's the beauty, of course, of that spherical radial symmetry, is that the moment you get outside of any spherically symmetric, radially symmetric spherical charge distribution, it immediately collapses onto that of a point charge. So I'm going to go ahead and draw that. And of course, this is a negative charge, so it's inward. I'll label this E2. And I'll go ahead and notice that I'm not drawing it inside. I'm just drawing it everywhere in the universe, but it finishes up on the that negative charge. So it's everywhere outside of the negative charge, but it's not inside the cavity. Now this is an opportunity. Oh, and I guess we'll do the same thing just with Q2 here. So plus Q2, same thing. It's completely symmetric. All the charge sits on the outside, and so that it would make no field anywhere inside of that, but it would make a field that starts on that positive charge and goes outside like that, and that's going to be E2 as well, because it's by charge 2, so on and so forth. So you can see why I'm using different colors here, because this is getting very mixed up. But just in summary, inside the cavity, only the black, okay? Only Q1 contributes. Inside the material itself, you have the black and blue, so only from Q1 and negative Q2. There should be only, if I drew this so that you can see, inside the material itself, there's black and blue only, and then outside there's all three. There's black, blue, and orange, okay? So they kind of progressively, you get one more field contribution as you go to each section, okay? So just as to summarize, if you're inside the cavity, you have only from Q1, so that is the black. when you're inside the material of the conductor, inside the material, you have that of Q1 and Q2. So you have black, and then you have the orange pick up. Sorry, blue. And I should specify here that that's the negative Q2 only. And then when you're outside the whole system, then you have the Q1, the negative Q2, and the positive Q2, which are black, blue, and now picking up the orange. So that's basically just writing down all this. Okay, so let's go ahead and analyze this. We know that the inside the material, E net has to be 0. That we know because, again, inside a material, perfect shielding. So if the charges felt any residual net field inside there, they would just polarize more until there wasn't, okay? So what's making that field? Well, it's Q1 and Q2, and Q1 is a point charge, and negative Q2, when you're, again, remember, when you're outside of that, that acts like a point charge. Well, what 2 point charges right on top of each other, right? Remember this, when you get outside, it behaves just like a negative Q2 right in the middle of that space. So a Q1, a positive Q1, and a negative Q2, what would the values be so that the net field would be 0? Well, we can safely conclude, therefore, Q1 is equal to Q2, okay? So I guess I should say just the magnitudes, of course. Q1 is positive and Q2 is negative. So remember, in general, it's hard to know how much charge needs to polarize to make the field 0, but here, because we have our symmetry, we can say, well, how much negative Q2 needs to go to the inner edge for that to exactly cancel off the field of Q1? Well, Q2, once you're outside, exactly acts like a point charge, so that and that, you need the 2 point charges to be equal. So we just had a big revelation that how much charge actually polarizes on this. I'm going to go ahead and scratch this out, okay? It's exactly the same as the charge in the interior. So if we really don't even need all these labels. We have plus Q in the middle, negative Q, same charge goes on the interior, and of course then that means if this whole body is still going to be neutral, it's still going to be a neutral conductor, then it's got to be Q2. Q2 on the outside is just Q as well. So all these labels are actually unnecessary. And what that means then is that we've safely concluded that the amount of charge on the inside of the inner edge of the conductor is actually the exact same amount as the charge that went on the inside to do the polarization. On your homework problem, it asks, well, what if the charge, just as an aside here, what if the conductor wasn't neutral, it already had charge as well? Well, this polarization would happen still, that we need to protect the interior of the conductor, and then we learn that any excess charge that does exist on the conductor has to exist on the outside. So that's a little bit of a hint. Well, I mean, that's pretty much giving it away, but that is one of the homework problems. So let's go ahead and figure out what this means then. That makes that so that the net field on inside this material is 0. So essentially, these two kill each other. Okay, they go whoosh, these two, the black and the blue, kill each other. And if that's the case, well, if black and blue cancel each other in the interior, nothing changes on the outside. They also cancel everywhere. Okay, so not just in the interior, but everywhere. And so the only field that's actually left, they cancel out here as well, the only field that's left on the outside is that of Q2, which again we said was just that of the exterior charge. So let me draw not all the individual contributors, but let me just go ahead and draw what's left. So I'm just going to call this plus Q. I'll draw in that cavity, or draw in the cavity here, and draw the neutral conductor around it, just to make it be less confusing again, where the material is. I'll kind of shade it in here. And what we said was that you have minus Q builds up on the interior, and plus Q builds up on the exterior surface of the conductor, plus Q. And let's take a look at the net field. Okay, well, on the inside of the cavity, it's just that of the point charge, like so, okay? You haven't picked up any other enclosed charge yet, so inside the cavity, you have the electric field is 0. Oh, sorry, not 0, just KQ over R squared. Okay, inside the material, you have nothing, perfect shielding. And on the outside, well, you pick up the plus Q again from the exterior. So outside the whole thing, you go back to KQ over R squared. Okay, and that is going to look like the field of a point charge that's collapsed right into the middle, where this, of course, already was. So let's go ahead and draw what this would look like. What would be the radial component? So I'm going to mark down 2 radii, the inner radius and the outer radius of the conductor are inner, I guess I'll call it Ri, I don't mean initial, I mean inner, and Ro, which is outer. So what does this look like? Well, inside, it's just that of a point charge, okay, just your good old KQ over R. Then it immediately jumps down to 0. We have that perfect shielding. And then outside is a point charge, so the question is, where exactly does it pick up? And I'm going to draw myself a little guideline here. It picks up exactly where that left off. Because let me remind you that when you're trying to talk about the field of this outer part, okay, that looks like exactly that of a field of a point charge collapsed in the middle, and it's at the same value, okay? So the moment, let me remind you again, the moment you get outside this charge, the field looks immediately like a point charge collapsed right to the middle, and so it basically looks like it picks up the field of this again, okay? So this is just, it just looks exactly like a point charge of Q, point charge Q. It just has this interrupted thing where the net field is 0 on the interior, okay? So really, of course, this is caused by the actual point charge plus Q, and here, this is caused by the plus Q that's on the exterior surface. So the source of this is actually different. This is the actual point charge, this is the plus Q charge on the outside, but it looks like it just picks up the electric field and runs with it exactly how it would have been if the conductor weren't there, okay? So that's kind of a cool thing. It's basically the field of a point charge with this stretch where we protect the interior material of the conductor from fields where the material actually is, okay? Now, what else can we do with this? Well, let me show you, go back to another trick that we did here. We did, of course, charging by induction. We grounded this guy. And what grounding does is wipes out half of the charge distribution. And so let's try that here. Well, what if we ground this? Well, same thing, it's going to wipe out this. Okay, so now this positive charge on the exterior, the most it can repel from this positive point charge inside is not just to the outer surface, it can just go right into the ground. And so we wipe that out. Well, if we wipe that out, actually let me do that in a different color here so that we can see. So the grounding part, I guess I'll do in purple. So that'll wipe that out. Well, that's what that's going to do. That right there is, of course, that is the charge that allows the field to continue on the outside. Okay, so again, if you go back and look over here, the black and the blue, right, the field of the inside point charge and the interior minus Q, they wiped each other out forever once you got from this point forward, and the only thing carrying on the field on the outside is orange, and now we've taken away that charge, so it takes away that field. So what that actually does is it makes it look like this. Same thing on the inside, same thing in where the material is, but then it just stays flat, okay? So that's the only difference. Let me see if I can make it clear here. That goes like this, like this, like this, but then it just stays flat. So the only difference is on the very outside. So, so what? What does that do for us? Well, let me point out something very interesting. If you have a point charge, normally its field goes off forever, okay? So if you have a point charge just out in space, there's nothing you can do short of going infinitely far away. You will always have a field of something, okay? But we've just said, if you take a neutral conductor and you put it around this thing, you can actually block the field from getting outside, okay? So we have actually just, what we have done here is we have shielded the rest of the universe from knowledge of the existence of that point charge. Okay, we've just put because we've surrounded it by a neutral conductor, and this is important, of course, that is grounded. Okay, so we have just developed a means of shielding the rest of the universe from knowledge of a point charge and its field. So this is actually a fairly useful thing to do. To give you some examples, you go back to your electric field hockey applet, right? If you remember that, there was a magic bin in the top of the screen where you had plus charges and there was another bin for minus charges, and they had absolutely no effect on the playing field till you drag them out. And then, of course, the moment you drag them out, then, of course, their fields extend throughout the playing field of the electric field hockey. And you might have thought, this is just a weird construction. This is like just a computer applet. It's not really possible to have some sort of device where you can put the charges in a box and not have to deal with their fields. But that's a very real thing. This could have been a neutral conductor that is grounded. Now, obviously, this doesn't have the necessary symmetry, but it turns out that the general gist of what I've said does work in general. If you put charges inside a neutral grounded conductor, then the fields of those will can be blocked from the environment. They actually use this, in practical applications. For instance, if you want to ship something that has charge, and you want them to not get their fields to not escape, you can ship it in a grounded container. And of course, it doesn't literally sit there being connected to electrical ground, but if it's a sufficiently large container, it can act as its own ground in some way. This is this kind of interesting idea that's possible because there's plus or minus charge. With gravity, for instance, we don't have plus mass and minus mass, but the concept would be the same. Okay, if you could put, say, like a planet inside this massive sleeve, you could, of course, block that planet from exerting any kind of gravitational pull on the rest of the universe. Of course, you can't do this kind of shielding because there's no such thing as plus mass and minus mass, but it's totally possible with charges, okay? This is just an example where I was able to exactly calculate the amount of charge polarization because I used Gauss's law and what I know about spherically symmetric, radially symmetric charge distributions. You notice that in the general case, figuring out the charge is very difficult. This was one of the few cases where it's actually quite simple to do that, and in fact, it turns out the amount of charge on the inner and outer surfaces is exactly the same amount, and the inner and outer surfaces, the neutral conductor, is exactly the same amount of charge as the charge you put on the interior that induces the polarization in the first place. Okay, so I think it's going to do it for this video.